Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. In the last lecture, in the topic of dynamics, fluid dynamics, we were discussing, or dynamics of fluid, we were discussing about the momentum principle and its applications. So, we have seen that in the case of steady state system, for a linear, with respect to the linear momentum principle, from the Newton's second law, we have derived the basic equation as say sigma fx is equal to rho q beta 2 vx2 minus beta 1 vx1, whereas sigma fx is the total force upon the control volume, external force on the control volume, that is equal to the linear momentum change with respect to system. So, this we have seen where beta is the momentum coefficient or momentum correction factor, as we have seen. And then we were discussing about the applications of momentum equations. So, we have seen that say the linear momentum principle we can utilize for various problems, like wherever to find out the force due to flow of fluid around a pipe, bench, enlargement and contraction, or we can use the principle to find out the force on a nozzle or the outlet of a pipe, or the impact of a jet, force due to flow around a curved vein, etc. These different kinds of problems we can use this linear momentum principle or linear momentum equations. So, that we were discussing the last lecture, and we have seen some of the applications. Say first case what we have discussed earlier was the force due to flow around a pipe bench. So, we have seen, say we will be considering as a basic steps, the basic steps involved are we will be considering control volume, and then we will be calculating the total force on the system, and including the pressure force, body force, and then we will be finding the resultant force, and then we will be equating with respect to the momentum change. That is what we have seen, and we have derived the equation for one of the example, say force due to flow around a pipe bench in the last lecture. So, now as a second case we will see here the force on a pipe nozzle. So, say generally we use, say a nozzle is used to say to create a jet, and then say we want to find out with respect to the nozzle what is the force coming upon the pipe where the nozzle is connected. So, as we have seen earlier, here also we will be considering a control volume. Say for example, here we are considering this particular problem. Say here you can see that a pipe is coming and the nozzle is connected, and the control volume considered is here. So, here the velocity of entry is u1 and the velocity of exit is u2, and the area of cross section entry at the entrance is a1 and the area of cross section at the entrance is a2. So, now the control volume considered is shown in this slide, and so with respect to the nozzle, the fluid is contracted at the nozzle and forces are induced upon the on the pipe where the nozzle is connected. So, first we will consider the total force. So, the total force Ft, or in the x direction we are considering now. So, Ft is equal to Ftx is equal to the mass of fluid, or rho into Q, where rho is the mass density, Q is the discharge coming from the pipe, into the velocity difference u2 minus u1, where u2 is the exit velocity and u1 is the entrance velocity. So, the total force with respect to this the nozzle, I will say, which is acting upon the pipe is F t is equal to, in the x direction, F t is equal to F t x is equal to rho q into u2 minus u1. So, here if you use the continuity equation, q is equal to a1 u1 is equal to a2 u2. So, from the continuity equation we can get the discharge, q is equal to a1 u1 is equal to a2 u2. So, hence we can write the full total force in the x direction, F t x is equal to rho q square into 1 minus a2 divided minus 1 by a1 as shown in this slide. So, like this we can find out the total force, and then say as far as the pressure force is concerned. So, here we have already found the total force with respect to the x direction. So, then next step is we will be finding out the pressure force. So, the pressure force F p is equal to, in the x direction, F p is equal to F p x, that is the pressure at 1 minus pressure at force at section 2. So, this is section 1, so here section 2. So, the pressure force, the effective pressure force is equal to pressure at section 1 minus pressure at pressure force at section 2. So, by using the energy equation or the Bernoulli's equation, we can write say with respect to the section 1 and section 2, we can write P 1 by rho g plus U 1 square by 2 g plus Z 1 is equal to P 2 by rho g plus U 2 square by 2 g plus Z 2 plus H f. So, here where H f is the losses due to the friction. So, here if we neglect the friction losses, so here then H f is equal to 0. So, that we can write the pressure force from the Bernoulli's equation. If we consider this particular case, Z, the datum head is same, Z 1 is equal to Z 2. So, the pressure outside is also here, when after the jet is say here the from the liquid is coming out of the jet. So, here the pressure is atmospheric. So that P 2 is equal to 0. So, that from the continuity equation we can write say here q is equal to a1 u1 is equal to a2 u2. So, finally, we can write P 1 is equal to rho q square by 2 into 1 minus a2 square minus 1 minus a1 square. So, this gives the pressure force. So, that means the pressure here P 1. So, at this section P 1 we get as P 1 is equal to rho q square by 2 into 1 minus a1 square minus a2 square. So, this gives say the pressure force. So, now this particular case is concerned, there is no body force. So, since the body force here we neglect. So, finally, the resultant force we can write as say the total resultant force is equal to F r x plus F p x plus F b x. So, body force is 0 and then P is the pressure force and F is the resultant force, which we have already found here. So, finally, we get the resultant force for the system F t x is equal to F r x plus F p x plus F b x, and finally, F r x is already can be written as F t x minus F p x minus 0. So, this is with respect to the F r x is obtained like this. So, now finally, F r x is equal to rho q square into 1 by a 2 minus 1 by a 1. So, here for which is obtained from the total force which we have already found F t x, and then the pressure force is concerned, we have already calculated rho q square 2 into 1 minus a 2 square minus 1 by a 1 square into a 1. So, this is gives the resultant force for the system. So, resultant force is equal to rho q square 1 divided by a 2 minus 1 by a 1 minus rho q square by 2 into 1 minus 1 divided by a 2 square minus 1 by a 1 square. So, where a 2 is the cross section at this location where the nozzle location, and a 1 is the cross section at this location at section 1. So, this gives the resultant force. So, this resultant force is the force which is acted upon with respect to the effect of this nozzle. The force coming on this the pipe is the force on the pipe is given by this resultant force. So, that force should be say that resist the with respect to the nozzle. This is the force which resists the when the nozzle is the liquid is passing through the nozzle. So, this is the case for the second case which we discussed is the force on a pipe nozzle as shown in this figure. So, this is the second case. So, now we will be discussing another case which is the impact of a jet on a plane. So, as we have seen there are a number of applications as far as the linear momentum equation is concerned. So, third case is the impact of a jet on a plane. So, here you can see that say a jet is coming and then impinging on a plate. So, say let us assume this case 3, the third case, say the jet is acting at 90 degrees. So, here you can see the jet is coming at 90 degree and then impinging on this plate, on the vertical plate. So, we want to find out the force on the plate or the reaction of the plate. So, this is what we want to find out with respect to this case, which is the third case, the impact of a jet on a plane. So, here you can see that the pressure force is 0, since you can see here everything is open to the atmosphere. So, the jet is coming through the atmosphere and then it is impinging on a it is hitting on a flat plate vertically placed. So, here say for example, if this is the plate and then the jet is coming like this vertically with respect to this plate. So, now say the pressure force here, all the pressure force is 0 or atmospheric, and then here this is the control volume which we consider here. So, the control volume is with respect to this plate and where the jet is impinging on the plate. So, this is the control volume, and the body force also in this particular case it is ignored. So, if we assume that the velocity here of the jet is u1 and then this is the velocity in this upward direction is u2 and the velocity in the downward direction is also u2. So, due to the symmetrical case here, but you can see here say with respect to here the body force is ignored, and then the total force here we will get. So, the velocity of approach of the jet is u1 and it is after hitting the flat plate, the velocity is u2 upward direction, downward direction. So, now the total force Ftx is equal to the rho q multiplied by u2x minus u1x. So, we are finding the force in the x direction of this direction. So, this is equal to total force is equal to Ftx equal to rho q into u2x minus u1x, the velocity in x direction after the jet is heated on the impinged on the plate, and u1 is the velocity of approach. So, here so now say this is equal to rho q, say here total force is equal to minus rho q into u1 x. So, here you can see that x direction is concerned. So, x direction is considered here. So, this plate is placed vertically. So, you can see here u2 is say the x direction, say u2 x is here it is 0, since x direction only the y direction velocity is there. So, u2 is in the y direction both upward and downward. You can see that x direction velocity u2 x is equal to 0, since the plate is placed vertically. So, that total force Ftx is equal to rho q into u2x minus u1x. So, u2x is 0. So, this is equal to Ftx is equal to minus rho q u1x, and then since due to the symmetry you can see that here the force on the y direction which is equal to Fty is equal to 0, so due to the symmetry. So, resultant force finally we can write that is equal to minus rho q into u1 x. So, this gives the resultant force. So, finally, for this particular case, this is a simple case where jet is hitting say at 90 degree on a flat plate. So, here we do not consider the friction on the plates, we assume that the plate is smooth. So, finally, what we get is the as far as the x direction the resultant force is concerned, it is given as minus rho q u1 x, where rho is the density of the fluid considered, q is the discharge of the jet discharge, or the say the discharge coming and hitting the plate, and u1 x is the velocity of approach in the x direction. So, this resultant force is obtained by is equal to minus rho q u1 x. So, this gives, so if a jet is hitting on a flat plate, so in the x direction, that is the resultant force. So, here that is equal to minus rho q u1 x. So, this is the third case. So, here we have analyzed the impact of a jet on a flat plate or on a plane like this. So, this is the third case. So, now we will be discussing the fourth case. So, fourth case is say here the application of the linear momentum equation is concerned. Fourth case is the force on a curved vane. So, you can see that many problems, say like say for example, we have a number of applications like say many cases jets will be coming and hitting on curved vanes like this. So, jet will be coming, jet action will be coming like this, and then it will be hitting on a curved vane like this. So, there are many practical cases where these kinds of problems occurs. So, now for this particular case we want to find out the force. So, now the jet is coming in this direction and we want to, so here this is the vane here and this is the jet. So, we want to find out how much is the force acted by this jet on this vane or the curved plate which we consider. So, here for this particular case say similar to the pipe pressures. So, here similar to the pipe. So, here the pressures are equal. So, you can see that here everything is atmospheric. So, we do not consider the pressure force. So, here pressure force is atmospheric. So, we can consider 0. So, which is very similar to the pipe case which we have seen. So, pressures are equal and it is atmospheric. So, and then the body force also in this particular case we do not consider the body force. So, here Fbx is equal to 0. So, now let us consider a control volume. So, here in this slide you can see a jet is coming and then it is deflected by a curved vane like this. So, this is the vane here and the jet is coming like this. So, here the velocity of the jet, incoming jet is say u1 is the velocity here, and then after deflected by the curved vane it is u2, and x direction is here and y direction is here, and the angle with respect to the where the velocity u2, this angle is theta with respect to this slide here. So, now say if we consider for this force on a curved vane, Fby is equal to, so that means the force, so here you can see that body force Fbx is equal to 0. So, in the x direction the body force is equal to 0 since x direction is here. So, and then the total force, now we can find out the total force here with respect to this particular figure here is total force is obtained in the x direction is equal to rho q into u2 minus u1 cos theta. So, here u2 is in this direction. So, here which is deflected, and then if you consider this as the normal direction. So, now the total force with respect to the x direction will be rho q into u2 minus u1 cos theta. So, here this is u2 and here this is the angle theta. So, u2 minus u1 cos theta gives the total force. So, total force in the x direction is equal to minus rho q into u1 minus u2 cos theta. So, finally, this can be written as that is equal to minus rho q square into 1 minus cos theta divided by A, which is the area of cross section. So, since U2 area of cross section of the jet which is coming here. So, since U2 is equal to U1 is equal to Q by A, where if the Q is the total discharge. So, this Q by A. So, that we can write say for this U2 and U1, we can substitute with respect to this Q by A. Finally, the total force is obtained, that is equal to minus rho Q square into 1 minus cos theta by A. So, this gives the force on a total force on the curved vane, and then finally total force in y direction say will be equal to, so Fty is equal to rho Q into U2 sin theta minus 0. So, here you can see that this is U2 sin theta, and here it is coming in this direction. So, effectively we here say this other direction it is not considered, there is no y direction, there is no velocity. So, that is Fty is equal to rho Q into U2 sin theta. So, this can be written as that is equal to rho Q square by A into sin theta. So, finally, we get Ftx the x direction, finally we can get Frx, that means the resultant force plus the pressure force anyway not considered here, body force. So, is also in the x direction, there is no body force. So, Ftx the resultant force Frx is equal to Ftx, and then here this with respect to the y direction Fry is equal to Fty minus Fby, and the resultant force we can find out, resultant is equal to square root of Fx square plus Fy square. So, this gives the resultant force on the curved vane. So, we say now we have seen various cases. So, first say the various cases, for first one is the impact on a jet on a plane, and now the second case, say the third case is impact, the first case is the force due to flow around a pipe bend, second one is force on a pipe nozzle, and third one we have seen is impact of a jet on a plane, and then fourth one is force on a curved vane, as here we have analyzed. And now the fifth case which here we will be discussing here is jets on turbine blade. So, you can see that many cases we will be analyzing, say say like Pelton wheel or say turbine problems. You can see that jet will be coming like this, the flow with respect to jet action, and then you can see that there will be a wheel with various vanes like this. And then you can see that due to the jet action it will start rotating. So, here it is we can use this, the principle of the linear momentum equation which we have seen. Here we can use the same principle to analyze the impacts of jet on turbine blades. So, here it is depicted in this slide here. So, the jet of in turbine, the jet of water is coming from through the nozzle like this. So, this is the jet of water, and then here the Pelton wheel is say mounted on an axle, and then due to the jet action you can see that a force is supplied, and then due to that the turbine wheel is rotating. So, here we will be having either this jet can be coming directly say 90 degree perpendicular to the vane, or it can be also inclined. So, here we will be analyzing how we can find out the force acted upon the jet on the Pelton wheel. So, here if you consider this U1, so most of the time you can see that this can be either say this plates which is attached with respect to the axle for the Pelton wheel. Most of the time it will be curved one like this. So, you can see here the curved say vane type mechanism. So, the jet will be coming say perpendicular to this like this, and then after that it is hitting on the plate say on the vane, and then it is deflected like this of velocity u2 on both direction, u2 this way and other way. So, the jet of velocity u1 is hitting on the vane and it is deflected say with a velocity u2 both direction back like this. So, this is the mechanism which is generally used in a belt and wheel. So, we want to find out the with respect to this jet action of how much is the force coming on the belt and wheel. So, that is what we want to find out. So, as you can see, so here the jet is coming perpendicular on the horizontal direction and then it is deflecting also on the horizontal direction. So, but it can be also inclined like this. In this slide you can see that here the jet is coming horizontal direction, but due to this the location or the nature of the vanes, you can see that it can be also deflected at an angle theta like this. So, here u2 is deflected in this direction and other way it is with respect to an angle theta. So, for this kinds of problem now let us consider say a control volume. So, as in the previous cases, so first we will be considering a control volume. So, the control volume is say here shown here. So, control volume is considered and then x axis is here, y axis is here. So, now again this case also here this particular case also we do not consider the pressure force. The pressure force is here it is atmospheric pressure or this 0, we consider the pressure force as 0, and then also the body force is not to be considered here in this particular case due to the specific nature of the problem. We do not consider the body force, and then you can see that finally the total force in the y direction will be 0 for this due to the symmetrical and due to nature of the particular problem here. The total force in the y direction will be 0, and then the total force in the x direction. So, if you consider this say if the jet is deflected at an angle theta like this. So, in the x direction total force in the x direction say that is the resultant force F T x, that is equal to. So, here with respect to this figure rho into q by 2. So, here say if the discharge is due to symmetry, let us assume that the discharge is q by 2 is passing, q is coming and hitting on this, and q by 2 is passing this direction and other direction also q by 2 is passing. So, F T x is equal to rho into q by 2 into u 2 x plus q by 2 into u 2 x minus q into u 1 x. So, q is the discharge coming to the hitting on the Pelton wheel or the turbine blade, and then the velocity back is u 2 at an angle theta. So, let us assume that in this particular case half of the discharge is going up this direction and other half is going down this direction. So, that the x direction, the resultant force in the x direction can be written as F T x is equal to rho into q by 2 as shown here. F T x is equal to rho into q by 2 into u 2 x plus q by 2 into u 2 x minus q into u 1 x. So, where u 1 x is the velocity in the x direction, u 2 x is the velocity in the with respect to x direction, and rho is the density of the liquid, or here if water is considered, then density of water. So, now the resultant force is obtained as F T x. So, here you can see that the u 1 x. So, the velocity is, say we are assuming for this particular problem the velocity is coming with respect to the x direction like this in this direction. So, u 1 x is equal to minus u 1 and then u 2 x. So, here you can see that u 2 x is equal to say u 2 cos theta. So, u 2 x is equal to u 2 cos theta. So, finally, the total the resultant force F T x is equal to rho q into say u 2 cos theta plus u 1. So, for this particular case F T s, the resultant force is equal to rho q into u 2 cos theta plus u 1. So, like this we can analyze say the force. So, here you can finally we have found the total force acting upon this say on this Pelton wheel or on the turbine blade. So, here we consider say, like in a Pelton wheel we have considered the turbine blade. So, how much is the force acted upon the turbine blade is calculated from this expression F T x is equal to rho q into u 2 cos theta plus u 1, where rho is the density, q is the discharge of the jet, u 1 is the velocity of the jet, and then u2 is the velocity after deflecting from the turbine blade. So, like this we can find out the force acted upon the jets on turbine, the force of jets on turbine blades can be calculated. So, this is the fifth case we have analyzed for the application of the linear momentum equation which we have seen. And now, the last case we will be discussing here is force due to a jet hitting an inclined plane. So, as we have seen the jet. So, if the plate here we have seen that whenever the plate is vertical placed, then the jet is acting like this. So, the analysis is very simple, we have already seen. We have analyzed here in the previous case, say the impact of a jet on a plane. So, the plane is placed perpendicular. So, the analysis is much simpler, but here in the last case here we discuss the force due to a jet hitting at an angle or at an inclined plane. So, if we consider a plane like this, so here a plane is like this, and then a jet is coming and hitting on the plane like this. Say the jet position is horizontal, jet is coming horizontally, but the plane is plate or the plane is inclined. So, here you can see in this slide how the mechanism is. So, this is also many problems will be of this kind. So, here the jet is coming with a velocity u1, and then it is hitting on an inclined plane. So, this with respect to the, say if we consider the normal to the plane which we consider. So, this is at an angle theta like this with respect to the horizontal. So, here the velocity of the jet is u1, and then in the previous case we have seen earlier that say if it is normally placed, the velocity will be same to the both sides as u2 and u2. But here you can see that due to the inclination of the plane, so the velocity to this direction u2 is the velocity in this direction, and then in the other direction it is u3. So, it is not symmetrical, or the plane is inclined, or so the velocity in this direction is u2, and the downward direction it is u3. So, here we consider the angle theta. So, now to analyze this problem, so we will be just considering this problem like this. So, here so the same plane what we consider, the jet is in the horizontal direction, and the plane is or the plate on which the jet is hitting is inclined. But then the same case we can in a very similar way we can consider the plane is vertical and jet is inclined. So, here you can see so the same problem, it is a very similar problem, very same problem. So, we are considering the plate is or the plane is vertical like this, and then the jet is acting inclined. So, we have seen the cases here. So, the actual case is the plane is or the plate is inclined and jet is coming horizontal. So, what we are converting this problem into, we place the plate as vertical, and then we consider the jet is acting inclined. So, that is the way which we are analyzing this problem. So, the diagram here, the diagram is rotated for analysis. So, now we can see, so this is angle theta, and u1 is the jet velocity is u1, and now x is in the horizontal and y is vertical direction, and u3 is the velocity downward, u2 is the velocity upward. So, now here if we use the Bernoulli's equation, so here say with respect to this figure we can see that P1 by rho g plus u1 square. So, as previous case we will be considering control volume. So, P1 by rho g plus u1 square by 2 g plus z1 is equal to P2 by rho g plus u2 square by 2 g plus z2. So, is equal to P3 by rho g plus u3 square by 2 g plus z3. So, if we consider 3 position here, here and here. So, 3 sections. So, from the Bernoulli's equation we can write P1 by rho g plus u1 square by 2 g plus z1 is equal to P2 by rho g plus u2 square by 2 g plus z2 is equal to P3 by rho g plus u3 square by 2 g plus z3. So, now here if you assume that height difference is negligible. So, with respect to the jet action, the height difference is not so much. So, we can assume Z12 is equal to Z2 equal to Z3 for analysis purpose, and then the pressure, the jet is say acting in atmospheric pressure. So, all pressure is atmospheric. So, that we can assume that here all due to atmosphere pressure, here we can see that u1 is equal to u2 is equal to u3. So, here the velocity say with respect to this particular problem, u1 is equal to u2 is equal to u3. So, now with the Bernoulli's equation, the possibility is that u1 is equal to u2, since the pressure is atmospheric. So, that is already all these terms are say gone, and then Z1 is equal to Z2 is equal to Z3. So, finally, we get the velocity. So, this is an approximation, u1 is equal to u2 is equal to u3. So, now from the continuity equation, you can see that if we apply the continuity equation, so the discharge, this should be what is hitting on the plate should be equal to what is going up and what is going down. So, Q1 is equal to Q2 plus Q3. So, for that we can write U1 plus A1 is equal to U2 plus A2 plus U3 plus A3, or we can write A1 is equal to A2 plus A3, or finally, we can write Q1 is equal to A1U or Q2 is equal to A2U, and Q3 is equal to what is going down, that discharge will be Q3 is equal to A1 minus A2 into U. So, Q3 is equal to A1 minus A2 into U. So, the pressure force since it is atmospheric, that is considered 0, and finally, we got Q1 is equal to A1U, Q2 is equal to A2U, and Q3 is equal to A1 minus A2 into U. And in this case also, we neglect the body force is ignored. So, finally, the total force Ftx in the x direction, the total force is equal to rho into Q2 into U2x plus Q3 into U3x minus Q1 into U1x. So, with respect to this figure here, finally, we get the total force in the x direction Ftx is equal to rho into Q2 into U2x plus Q3 into U3x minus Q1 into U1x. So, here say here in the with respect to this, after the figure is rotated here, you can see that the x direction U2x and U3x are 0. So, U2x is 0, U3x is 0. So, we get U2x is equal to U3x is equal to 0, jets are parallel to the plate. So, finally, this expression become since U1x is equal to U1 cos theta. So, this angle is theta. So, U1 x is equal to U1 cos theta. So, finally, we simplify the equation to Ftx, the total force in the x direction is equal to minus rho Q1 U1 cos theta. So, this will be the force acted upon by this inclined jet on this plane, or this particular case which we consider the plane is inclined and the jet is horizontal. So, finally, the expression is the total force is Ftx is equal to minus rho Q1 U1 cos theta. So, like this we can analyze what will be the force due to a jet hitting at an inclined plane, or say a jet, the plane is vertical and a jet is inclined. So, that both cases we can analyze. So, finally, the resultant force exerted on fluid is equal to so body force is neglected, pressure force is atmospheric. So, that we do not consider. So, in the x direction Frx is equal to minus rho Q1 U1 cos theta. So, this is the resultant force exerted on the fluid, and then in bidirection Fty, you can see that Fty is equal to 0 in this particular case. So, finally, the resultant force is R is equal to minus Frx, which is the reaction, or which is the with respect to the jet, what is the force acted by the plate. The reaction force will be say R is equal to the opposite direction minus Frx. So, that is equal to rho Q1 U1 cos theta. So, this gives the reaction force the opposite direction. So, that is minus Frx. So, like this we can analyze the resultant force acting on by a jet heated on an inclined plane. Also, from the what we have seen so far we can also find out the discharge say in each direction Q1, Q2, Q3 that we have seen here. So, that also can be calculated. Discharge goes on each direction, can be also found in a very similar way. So, this is the sixth application we have discussed. So, what we say now, we have seen the from the Newton's second law we have derived the linear momentum equation, and then we have seen various applications in this. So far we have discussed various applications. So, now we say from the applications we can see that some of the interpretations what we can say with respect to the applications are. So, we say here the linear momentum, say we have to always consider the direction. So, whether it is x direction or y direction. So, that we can say that the linear momentum is direction. So, that is obvious, always we have to say which direction it is acting. So, the linear momentum is direction. So, that is the first interpretation, and then the most of the cases we have discussed is at steady state condition. So, for steady state flow the time rate of change of momentum is 0. So, that is not considered. So, most of the examples we have considered is at steady state condition, and then also we have seen we are using the Newton's second law. So, we are considering the external forces. So, we have to consider the sign, that means whether the force is acting which direction, whether say plus or minus, the sign is important. So, we have to consider the external forces, we have to consider its sign. So, algebraic sign of the external force to be considered, and also here as far as the control volume which we consider. So, the analysis is, we are starting the analysis by considering control volume. So, for the control volume considered, only external forces acting on the control volume to be considered for the problems which we have seen here, and then say also in a very similar way. So, the cases, the examples which we have analyzed is, say most of the time the plate or the vane, all the cases say this they are fixed. So, it is not, the vanes or the plates are not moving, but also the linear momentum equation we can write in a very similar way for moving control volume. So, here you can see that the plate which we considered with respect to the jet is. So, now the jet is coming and the plate is fixed. So, we have found the force. So, but if the plate is moving like this, so when the jet is acting, the simultaneously the plate is also moving. So, that is the case where the moving control volume. So, here the cases which we have considered so far is fixed control volume, but some cases like we have seen when the wheel is rotating. So, it is moving control volume, or when the plate is moving with respect to the jet action. So, then we can see that the case is of moving control volume. So, we have to consider, so now jet is coming. So, in a very similar with respect to the jet movement, the control volume is also moving. So, the linear momentum equation can be transformed with respect to the moving control volume. So, for the moving control volume, say like moving plates and vanes. So, when a jet with velocity v strikes a plate moving with velocity small v, so fluid mass is no longer the fluid mass strike on a stationary plate. So, as I mentioned, so if the velocity here a plate is there and the velocity of the jet is, say here v, capital V is the velocity, and then the plate is now moving with a velocity of small v. Now as earlier case, for the fixed plate, it is not the same, it is not the same mass that is hitting the plate as in the case of a stationary plate, since the plate is also moving. So, here this is the plate, the initial position, and now jet is coming and hitting like this. So, now but after some time you can see that the plate is moving. So, the mass is changing, the fluid mass is no longer the same, the fluid mass strikes on the station with respect to stationary plate, but now the plate is shifted with the, so the plate is moving with the velocity say small v meter per second, and the jet is of capital V meter per second. Then we will be finding out the say the mass which really overtakes the plate per unit time. So, we have to see that the relative velocity we have to consider and what mass will be overtaking the plate per unit time to be considered when the plate or the vane is moving. So, we have to consider the relative velocity. So, here we can see that capital V minus small v will be the relative velocity. So, that will be used in the calculation. So, in the next slide, so here we can see that say for the mass striking the plate is area of cross section of the jet. So, if jet has got an area of cross section small capital A and then density is rho, then relative velocity we have to multiply absolute velocity V capital V minus small v. So, we have to find out the relative velocity. So, mass striking the plate is so Q is equal to area of cross section into rho into V minus small v. So, the velocity of the jet minus the velocity of the plate or the vane we consider. So, the calculation the relative velocity should be used. So, with reference to this we will be discussing few of the examples. So, here the first case is we consider a problem like this. So, here there is a curved vane or a plate or a cup like this and then a jet is coming and hitting on the vane or the cup, and then the vane itself or the cup itself is moving with a velocity. So, we want to find the work done per second by the jet on the cup. So, the problem statement is as shown in figure. So, here figure 6 centimeter diameter jet of water impinges. So, here the diameter of the jet is 6 centimeter. So, 6 centimeter diameter jet of water impinges on a series of hemispherical cups and is deflected through 180 degree. So, the jet is deflected by 180 degree. The velocity of the jet is 10 meter per second and the cup is moving at a velocity of 4 meter per second in the x direction. Calculate the work done per second by the jet on the cups. So, here you can see that the jet is coming in this direction and the cup is or the vane is placed, a curved vane is placed like this, and it is moving the cup or the vane is moving with a velocity of 4 meter per second. The jet velocity is 10 meter per second, and if u1 is the jet velocity, then you can see that it will be after the jet reaches the cup, it will be deflecting and it is deflecting at 180 degree. So, u3 is the velocity in this direction and u2 is the other downward direction. So, you can see that since we consider the atmospheric pressure here, so u1 is equal to u2 is equal to u3 for this particular problem. So, we want to find out the work done per second by the jet on the cup for this particular problem. So, now since the jet is moving with a velocity of 10 meter per second and the cup is moving with a velocity of 4 meter per second, the relative velocity of jet is equal to 10 minus 4, that is equal to 6 meter per second. So, here also this particular problem we do not consider the friction. So, no friction is considered. So, the mass of the fluid striking the cup per second is say the diameter of the jet is given. So, that is 6 centimeters. So, area of cross section of the jet is pi by 4 into 0.06 square into say pi d square by 4 into the velocity is 10 meter per second and then density is 998. So, finally, we get 28.217 kilogram per second. So, this is the mass of fluid striking the cup per second. So, now we want to find out the force exerted by fluid on the cup. So, that is obtained with respect to the equation we have derived. So, we can write that is equal to the force exerted by fluid on the cup is equal to minus q rho into the velocity change or the relative velocity. So, you can see here with respect to the figure. So, it is both directions. So, we have to consider with respect to both directions. So, you can say here you can see the force exerted by fluid will be minus q into rho, where q is the discharge, rho is the density, into minus v minus v minus v minus v. So, that 2 times. So, here you can see it is coming both ways. So, that is equal to we have already found the mass of fluid striking the cup is 28.217. So, into 2 times into the the relative velocity we have calculated is 6 meter per second into 6. So, that gives us 338.61 Newton. So, this is the force exerted by fluid on the cup is 338.61 Newton. And now finally, work can be found by, so here you can see that work is the force in work is equal to force in displacement. So, you can see that the with respect to the cup is moving at 4 meter per second. So, that we can write. So, the work done per second is the force exerted by fluid on cup multiplied by, that is 338.61 multiplied by this 4 meter per second, which is the movement of the cup. So, into 4 divided by 1000. So, that will give 1.3 by 1.354 kilowatt. So, this gives the work done per second for this problem. So, here we have analyzed a problem with which is say relative movement where the vane or the cup is moving with respect to the jet action. So, here what we have to see, we have to note here is we have to calculate, say while finding out the discharge, say while finding out the force which will be discussing the force exerted on the cup. So, that we have to say with respect to the relative velocity we have to consider. So, the relative velocity is considered here in this particular case, since the cup is also moving in the direction of the jet. So, this is the first example for first problem, and the second example is, here we will be considering another example. Second case is say for the with respect to an inclined say a jet is hitting an inclined plane. So, here the problem statement is as shown in figure. So, here you can see the figure here as shown in this figure. Say a jet is hitting on an inclined plate like this. So, we have to find say water jet to 5 centimeter having a velocity of 8 meter per second impinges on a smooth plate at an angle of 40 degree to the normal to the plate. So, we have to find out the impact of the jet when the plate is stationary, case A, and case B when the plate is moving in the direction of the jet at 3 meter per second. Also calculate the work done per unit time in both cases. So, here the problem is, so we have a say a plate put at an inclination of 40 degree with respect to the horizontal. So, that and then a jet is hitting or impinging on the plane at 40 degree. So, we have to find out the impact of the jet. So, we have to find out the impact of the jet when the plate is stationary. So, plate is say not moving. So, that is case A, and the case B is when the plate is also moving in the direction of the jet at 3 meter per second. So, here it is only given that the diameter of the jet is 5 centimeter. So, and also since as we have seen in the previous discussion, for all the pressure force, the pressure is atmospheric. So, we can say that U1 is equal to U2 is equal to U3. So, U1 is the jet velocity, U2 is the upward direction, U3 is downward direction. So, U1 is equal to U2 is equal to 8 meter per second, which is given value, and this angle is given as theta is equal to 40 degrees. So, as we discussed, we will be considering a control volume as shown here. So, this is the control volume which we consider. So, from the previous expression which we have derived, the impact of the jet is obtained as resultant force exerted, that is equal to rho q into u1 cos theta, where rho is the density of the fluid, q is the discharge of the jet, and u1 is the velocity and angle theta. So, the impact the impact of the jet is equal to rho q into u1 cos theta. So, now then the impact can be calculated for case A when the plate is stationary. So impact is equal to rho q into u1 cos theta. So rho is 998 into q is pi by 4 into the diameter of the pipe jet is 0.5 centimeter. So into 0.05 square into u1 is 8. So into 8 into 8 cos 40. So this gives the impact. So finally we can see that the impact on the plate will be 96.07 Newton in the direction, say here in this direction. So this is the Fn. So this is in this direction. So this gives the impact of the jet on the inclined plane, that is 96.07 Newton. And then work done, here you can see that the plate is stationary. So since there is no displacement of the plate, so work done is force in displacement is 0. So work done here in this particular case is 0. And case 2, when the plate moves in the x direction, so v is equal to 3 meter per second. So if you consider the normal direction and relative velocity, so you can see that the relative velocity will be, the plate is moving with 3 meter per second and the jet velocity is 8 meter per second. So that is equal to 8 minus 3 is equal to 5 meter per second. So now the impact of the jet will be say impact is equal to rho into qr into u1r cos theta. So rho is 998 into pi by 4 into 0.05 square, that gives qr into 5 into 5 cos 40. So that gives 37.53. So this will be impact for whenever the plate is also moving with respect to the movement of the with respect to the jet force. So the relative velocity will be 8 minus 3 into 8 minus 3, that is equal to 5 meter per second. So with respect to when the plate is also moving, the work done W is equal to this the force into say the displacement per unit time. So here 37.53 into cos 40 into 5. So that gives 143.75 Newton meter per second. So this is the work done. So like this, say we can solve most of this problem by considering the linear momentum equation for either for a fixed control volume or for a moving control volume.